Chapter 11 homework problems we did right before break. I want to make sure you have the solutions available to you. Those were with energy and work. We went over a fair number of those in class. We did not go over this number 41, however, which took me a whole page. And I think there's a lot of things in there that are super useful. So as I paged through my textbook to figure out and look at the solutions or look at the question, basically you were given this graph here. You're told you had a 0.5 kilogram projectile or particle starting at 0 and 0 velocity and 0 position. It's asking you to draw graphs and plot of things based on information that's given. So you were given that there was a velocity time graph going from 0 to 20 meters per second in 2 seconds, back down to 10 meters per second after 3 seconds, and then holding steady at 10 meters per second. So the first thing you're asked to do is figure out the acceleration time graph. So this is simply the derivative of this, meaning you get the slope of the velocity graph to get the acceleration graph. So the slope is 10, then the slope is negative 10, then the slope is 0. For B, you're asked to find the position versus time graph. Well, there's a couple ways you could do that. One would be look at the area or the integral of this velocity time graph at every second, and then that area would tell you where you're located after that much time. So for example, 1/2 times 10 times 1 would be 5 meters. The other way you could do this is you could think about that x equals 1/2 at squared. Well, if you've got 10 meters per second squared, 1/2 times 10 times 1 squared would be 5 meters. Here, this area, 1/2 times 2 times 20 will be 20 meters. The same way here, if I look at this, 1/2 at squared, 1/2 times 10 times 2 squared, 2 squared is 4, times 10 is 40, times 1/2 is 20, gets us 20 meters. So I just ended up using either one of those methods, and I had to do this piecemeal if I did the graph, because I could not use the equation, just a simple equation. I would have to use, again, a piecewise equation if I wanted to do it that way. So I think I ended up using just the area of the graph for all these. So I ended up getting 5, 20, 35, and 45 meters. And my position time graph looked like this. The kinetic energy versus time graph. Kinetic energy, 1/2 mv squared. We knew the velocity at the end of those times, so I ended up doing that. If you notice, it's exponential here, exponential decay here, and then constant. So it's very peaky. For letter D, it's asking about the force versus time. Well, if we know acceleration versus time and we know the mass and we use Newton's second law, so we take the acceleration multiplied by the mass of 0.5 kilograms. So I get the exact same pattern of the graph, 5 newtons and negative 5 newtons. For letter E, you're being asked to use your force versus time graph to determine the impulse delivered. Well, the impulse is the area or the integral of a force versus time graph. So here, if I look at this from 0 to 2 seconds, I've got 5 times 2, that's plus 10 newton seconds. The impulse from 2 to 4 really is only a change from 2 to 3, so it's negative 5 times 1, so that's negative 5 newton seconds there. And so overall, that's the impulse during those time intervals that were requested. For part F and G, F is saying using the impulse momentum theorem, determine the particle's velocity at 2 seconds and at 4 seconds. So we know it's moving 0 meters per second to start, and impulse is change in momentum. So we have 10 newton seconds equals m times delta v. Well, we have that 0.5 kilograms, so we get a delta v of 20 meters per second. The delta v from 2 to 3 seconds, because we have a negative impulse, would be negative 10 meters per second. So the speed, or velocity rather, after 3 seconds would be 10 meters per second. That agrees with everything we've seen so far. The next thing is drawing a graph of force versus position. So essentially what we do is we need to think about our maximum position, which is 45 meters. So I made this 0 to 50 meters. And the force was going consistent for the first 2 seconds. After 2 seconds, our position was 20 meters. So I had 5 newtons times 20 meters. At 20 meters, and until we had 3 seconds, and that was at 35 meters, we had a negative force of 5 newtons. So I have something like that, where I have negative 5 newtons times 15 meters of displacement. So I have something like that for my force versus displacement graph. As you can imagine, that's going to represent things with work. So plus 100 joules of work done from 0 to 20 meters, or 0 to 2 seconds, negative 75 joules of work done from 2 to 4 seconds, and all that actually occurred from 2 to 3 seconds. So using the work is equal to work and mechanical energy theorem, work energy theorem, I guess. They said work kinetic energy theorem, I guess, to determine the particle's velocity at 2 second and 4 second. Well, if we gain 100 joules, that means we would have 100 joules of kinetic energy, 1/2 mv squared, 20 meters per second. From 2 to 3, we lost 75 joules, so we have a net of 25 joules total. 100 after 2 seconds minus 75 from 2 to 3 seconds, so 25 joules equals 1/2 mv squared. That equals 10 meters per second after 3 seconds. So the whole point of all this is that whether you think of work or energy or momentum or impulse or force or velocity, all the physics is the same. There's different ways to look at it, and they should all agree with each other. So I thought this was a pretty powerful problem. Problem 42, you had something that was basically accelerating an elevator up 1 meter per second squared for 10 meters starting from rest, asking about the work that gravity did, the work, the tension in the elevator cable, use work kinetic energy theorem to find the kinetic energy of the elevator, and then the speed. So essentially, gravity is acting downward even though the elevator is moving upward. So we have a coast of 180 degrees, so that's negative 98,000 joules. The tension would have to be 10,800 newtons because we need 1,000 kilograms accelerating up at 1 meter per second squared. So we need 1,000 newtons of net force. So the tension of 10,800 newtons times 10 meters is that much work done by the cable. So we have a net of plus 10,000 joules. So then we can figure out the speed of the elevator at the end. 10,000 joules of kinetic energy, 1/2 mv squared. 45, I think we went over this in class. The key thing here is that the wind acted horizontally, but if the person is going down the hill, that means that the wind, only a component of the wind is acting to slow the person down. I think someone in class gave me a different example of how to apply that, which worked out fine trigonometrically, but I did something like this. The spring pushing something up the hill, and then there was a sticky spot. So initially it did make it up this 1 meter distance to the truck bed at 1.7 meters per second. Again, EI equals EF. Initially you have spring energy, at the end you have kinetic energy and gravitational potential energy. But if you have work done by friction, we're going to lose that amount of work from the initial spring energy. So we only have 19.56 joules mechanical energy left, and you need 19.6 to make it to the truck. So it would almost make it, but not quite. This one I think we went over in class. I basically had to do some mathematical substitutions here, thinking about the fact that for part A, the velocity right after this, EI equals EF. I'm choosing this as my zero height position. So it's just spring energy equals kinetic energy. But then it's asking how high this goes up. So I need to take into account the fact that there's gravitational potential energy here. So I choose my zero height position at the bottom. So therefore the initial energy is going to be this energy of the spring plus the gravitational potential energy. Then we're going to be losing energy due to friction going up this slope. So that's mu mg cos theta times distance. So that's basically minus the work done by friction. And then that would equal mg h2 here. But that's too many variables. So I needed to put this in terms of d. And so basically d sine theta is equal to h2. So d is equal to h2 over sine theta. h2 is equal to d sine theta. Work that around and end up getting, would slide up 32.1 meters up the slope. So that's just a bunch of algebra there. And again, hopefully those make sense.